Objects orbit, comets flare, and scientists expect predictable behavior. Then 3I Atlas arrives and throws the rulebook out the airlock. When astronomers first spotted 3I Atlas, it looked like a routine interstellar visitor, a point of light on survey images, but follow-up observations changed everything. High-resolution imaging from the Vera C. Rubin Observatory and the Hubble Space Telescope showed the object was far larger than the early estimates, by miles. The nucleus size was revised upward, forcing NASA and ESA teams to reclassify what we're actually looking at. This isn't a small chunk of ice. It's a massive interstellar object that behaves nothing like comets we know. Size is not a detail. A bigger core means more mass, greater volatile reserves, and a different thermal profile when sunlight warms it. It alters how the object will respond to the sun, how long it can stay active, and how dangerous or scientifically valuable it might be. What began as a discovery notice quickly became a global observing campaign because a larger object simply changes the math on everything: brightness, detectability, and the potential for unusual behavior. And the behavior is unusual. Atlas is hyperbolic. It didn't form here. It came from another star system that alone places it in a rare category. But beyond origin, its chemistry and activity are puzzling. Water emissions, tiny active areas, almost no dust tail, and now reports of metal vapor signatures. Put the size, origin, and chemistry together, and you get something more than a comet. You get a relic from another era of our Galaxy S history. Scientists call it a time capsule, a fragment that formed before our sun, carrying chemical and physical clues from a different stellar neighborhood. For the watching public, here's the clean takeaway. We're not looking at a textbook comet. We're watching a visitor that rewrites questions about formation, lifespan, and composition of interstellar bodies. And because it's larger than thought, our window to study it just widened. The stakes for new discoveries are higher. Strange metal emissions, nickel with no iron. Now the real shock, spectral measurements show metallic emissions coming off Atlas, notably nickel, with iron either absent or far weaker than expected. That's not a small anomaly. In normal comet chemistry, nickel and iron are produced together. Seeing nickel vapor without iron forces scientists to reevaluate formation scenarios and long-term processing. Multiple observatories reported nickel lines in spectroscopic data, while iron lines remained essentially missing. Some teams even quantified surprisingly high rates of nickel release in localized jets. On Earth, nickel carbonyl is an industrial molecule. In space, seeing nickel bound with carbon or emitted alone is unprecedented for a comet-like body. So, what could cause it? There are a few working hypotheses, each with enormous implications. 1. Atlas formed in a metal-poor environment, a protoplanetary disk that never built up iron in the expected ratios, meaning its raw materials were enriched in elements like nickel relative to iron. 2. Billions of years of cosmic ray processing selectively altered the surface chemistry, stripping or hiding iron-bearing compounds while leaving nickel-bearing compounds accessible to sublimation. 3. Chemical reactions between exotic organics and metal-rich grains produced volatile metal compounds that vaporize under solar heating. None of these explanations is trivial. Each would revise our models of planetary system chemistry or long-term interstellar processing. The community is treating the nickel signal as a high-priority anomaly. Teams are rechecking calibrations, cross-validating with independent spectrometers, and running lab simulations of metal-bearing ices under cosmic irradiation for you watching. This is the kind of discovery that changes textbooks. Nickel without iron isn't clickbait, it's a scientific red flag. If the finding holds, it means at least some bodies in the galaxy form or evolve in ways we didn't expect. That opens new questions. How common are such compositions? Could they point to whole classes of objects we've missed? And most urgently, what will the next set of spectra show as Atlas moves through the inner solar system? Composition Deep Dive: What the Spectra Really Say. Let's cut straight to it. The chemistry coming off 3I Atlas is not what astronomers expected. Multiple teams pointed spectrographs at the object and read signatures that looked like water vapor and simple organics. That part is normal for comets. The surprise comes from the metal lines. Reports show strong nickel features, while iron, usually present alongside nickel, is weak or missing. That pattern forces real uncomfortable questions about how and where this object-formed spectroscopy is. Detective work. Light from the coma is split into fingerprints, emission lines, that tell you which atoms and molecules are present. Observers at Keck and other facilities reported nickel lines at visible and near IR wavelengths. Subsequent papers and preprints examined the spatial profiles and confirmed metal release in localized jets. Those findings aren't a single noisy measurement. They repeat across instruments and nights, which is why the anomaly stuck. What could create a nickel-rich but iron-poor signal? There are three leading data-driven possibilities. Primordial difference in formation. Atlas might have formed in a protoplanetary disk, chemically poor in iron, but comparatively enriched in nickel-bearing compounds. Early generation star systems, ones that formed before multiple rounds of stellar nucleosynthesis, can show unusual element ratios. If Atlas came from such a system, its bulk chemistry would look foreign to us. Selective processing during interstellar travel. Billions of years in interstellar space expose surfaces to cosmic rays, UV, and micrometeorite abrasion. Those processes can alter surface chemistry, perhaps destroying or burying iron-bearing phases while leaving nickel compounds more volatile or exposed. Laboratory simulations show radiation chemistry can radically change spectral signatures over long timescales, exotic surface chemistry or volatile metals. Some complex organics can form metal carbonyls or volatile metal compounds under the right conditions. If nickel is locked into a volatile carrier that sublimates at moderate heating, you'll see nickel vapor without the expected iron. None of these options is proven yet. They're hypotheses that fit the repeated spectral data. That's why follow-up is urgent. Higher resolution spectra, multi-epoch monitoring, and laboratory analog experiments will either confirm natural pathways or force an even stranger explanation. For viewers, the spectra are the raw evidence. Interpretations follow, and they must be checked. This is how science moves from weird to understood. The Mars images, NavCam stacking, and the missing tail. You saw the viral image, a neat, elongated light across the Martian sky captured by Perseverance's NavCam. It looked structured, tailless, and almost deliberate. That single frame lit up social feeds. But science looks at the full data set, not a thumbnail. First, the image processing reality. NavCam produces many short exposures. To reveal faint objects, teams often stack frames, align and combine them to boost signal. If the object moves between frames or alignment, assumes a stationary background, stacking can smear a point source into an elongated streak. Harvard S. Avi Loeb and others flagged that the elongated cylinder could be a stacking artifact, especially because the NavCam sequence covered many minutes, while Atlas moved relative to the rover's viewpoint, but stacking alone doesn't answer the bigger question. Why is there no long dust tail? Independent observations from orbiters, large ground telescopes, and space assets report a compact coma and minimal dust. In the standard comet model, sunlight heats surface, ices and launches both gas and dust into a long tail. Atlas shows water emission, but not an extended dust trail. That pattern appears in different instruments with different observing geometries, which argues against the whole phenomenon being a single camera trick. Possible explanations that fit the multi-instrument record. Sealed crust hypothesis. Atlas may have a thick, radiation-hardened crust that traps dust, while allowing some gas through microfractures, producing vapor but little particulate escape, localized venting. Outgassing confined to tiny active spots could eject gas without lofting significant dust. Small jets don't always form large tails, particle size effect. If the ejecta are dominated by very fine molecules or extremely small grains, radiation pressure and observation geometry can make a visible tail hard to detect at typical wavelengths. What this means for your viewers: the Martian NavCam image may exaggerate shape because of processing, but the global absence of a classical tail is real data from multiple platforms. That's the key science takeaway. One image grabbed attention, many datasets changed the story. The next steps are reprocessing raw frames with different motion models, stacking strategies, and targeted high-sensitivity imaging to settle whether the apparent structure is instrumental, geometric, or a genuine physical property of Atlas breaking the timeline. Atlas is older than the Sun. Listen. This is the part that turns a weird visitor into a cosmic artifact. Multiple lines of evidence point to 3I Atlas being older than our Sun. That's not drama, it's data. Isotopic ratios, elemental makeup, and the object S physical resilience all line up with an origin in a much earlier galactic era, roughly 7.745 billion years ago, long before our solar system formed. Why that conclusion matters: isotopes are clocks, ratios like deuterium to hydrogen, and specific oxygen isotopes were vary depending on the generation of stars that seeded a protoplanetary disk. Atlas S fingerprint doesn't match the family of comets we know that formed inside the Sun S natal cloud. Instead, its chemical signature looks like it formed from gas and dust that had a different enrichment history. Material produced by earlier, possibly lower metallicity stars. In plain terms, its ingredients come from a different kitchen. There's more than chemistry. Its survival through billions of years of exposure to cosmic rays, supernova remnants, and close stellar passages implies an unusually robust surface. That radiation processing likely built a thick, carbon-rich crust that protected volatiles underneath. That same armor explains why Atlas is only partially active today, and why its visible behavior contradicts modern comet models that assume fresher, less processed surfaces. Professor Brian Cox and other experts call objects like this galactic fossils. They carry molecular evidence of environments and star formation episodes that predate our Sun. If Atlas truly formed 7.5 billion years ago, then every molecule we measure is older than Earth, older than the earliest rocks, and older than the Sun's light. That makes every spectrum and every image a piece of galactic history. Not just astronomy, but archaeology on a cosmic scale. The implications ripple out. Models of early galactic chemical evolution will get new constraints. The ways planetesimals form and migrate in early star clusters will be re-examined and practical. An object older than the Sun that still contains water ice tells us the early galaxy had stable reservoirs of volatiles, shifting how we think about where life-building materials could originate. So, when you hear older than the Sun, don't treat it as hyperbole. Treat it as one of the hardest kind of scientific claims, a conclusion built from repeated, independent measurements, cross-checked against models. Atlas is a messenger from a time when the Milky Way looked very different, and we're re-unwrapping that message now. What comes next? Observations, labs, and the clock that's ticking. Right now, the race is on, and there's a clock. 3I Atlas is moving. The observation window is finite. Scientists worldwide have a checklist, and it's brutally practical. Verify, map, model. Verify first. Independent teams must replicate the metal line detections with different instruments and observing techniques. That means high-resolution spectroscopy across optical and infrared bands using Keck, VLT, Hubble, JWST where possible, and any facilities that can secure time quickly. Spatially resolving where the nickel and CN emissions come from in the coma is critical. Are they narrow jets, broad plumes, or spatially diffuse? The answer distinguishes surface chemistry from processing artifacts MAPI. Observatories will create time series maps of emission rates. Does nickel release increase as Atlas nears perihelion? Does it correlate with water outflow or with specific rotation phases? Mapping also means multi-angle views. Earth, Mars, orbiters, and deep space assets can triangulate the geometry and rule out line-of-sight surprises model. Lab teams will sprint to reproduce possible carriers, nickel carbonyls, and related organometallics under simulated interstellar radiation. Physicists will refine thermophysical models for a large, crusted nucleus with localized vents. Astronomers will fold non-gravitational accelerations from jets into orbital predictions to sharpen ephemerid's planum. If the anomaly persists, mission planners will dust off rapid response concepts, flyby intercepts, small fast chasers, or piggybacked instruments on existing spacecraft. Even if a dedicated mission is years away, the community will produce concrete mission requirements: what mass sample to capture, what instruments to include, whether to prioritize dust collection or compositional analysis. Communicate crucially. Agencies must keep the public informed with raw data and calibrated interpretations, not speculation. As excitement builds, transparency prevents misinformation and keeps scientific discourse focused on evidence. For you watching, expect a week-to-month cadence of new data releases. This is real-time science, sometimes messy, often iterative, but always self-correcting. If the nickel story survives peer review, we'll be rewriting textbook chapters. If not, we still learn about measurement pitfalls and the limits of rapid interpretation. Either outcome advances knowledge. Either way, this comet is doing what science loves most, forcing us to look closer, think harder, and test harder.